On a wooden inspection bench, the weldgun lay unloaded. Paper tags listed caliber, action, and magazine pattern. The handwriting aligned with the established Birmingham small arms practice. Ink numbers matched a ledger page in the workshop office. The weapon existed as a response to a request. Special Operations Executive Staff wanted a compact submachine gun. The request specified 9x19mm for supply convenience. Enemy stockpiles could supplement constrained British production runs. Birmingham Small Arms engineers proposed the Wellgun in 1942. Station 9 took responsibility for trials and field feedback. The Well prefix referenced the Welwyn facility location. The prototype was labelled as a machine carbine. Design sketches presented a short tubular receiver. A simple blowback bolt reciprocated within that tube. The bolt fired from the open position for cooling. Drawings showed no separate charging handle slot. Instead, the rear receiver carried a ribbed sleeve. The operator gripped that sleeve to retract the bolt. The bolt locked to the rear on the sear. Releasing the trigger allowed the bolt to run forward. The sleeve concept aimed to reduce external projections. A standard side-mounted handle risked snagging in containers. The sleeve allowed a smooth profile during carriage. It also reduced openings for dirt and debris. The mainspring sat forward around the barrel shank. This arrangement left the bolt body relatively compact. A guide ensured the spring remained concentric in operation. Armourers could withdraw barrel and spring as one unit. With the stock extended, length approached 27 inches. A weight empty remained under 7 pounds recorded. The barrel measured just under 8 inches long. Rifling used 6 grooves with right-hand twist. A hinged butt assembly folded beneath the barrel axis. When folded, overall length approached 17 inches compressed. This suited containerized drops from aircraft over occupied territories. Packing lists referenced Wellgun pieces alongside Sten carbines. The Wellgun retained the familiar Sten pattern magazine. A 32-round single-feed box seated vertically below. The magazine housing sat on the centreline, not sideways. This simplified storage and improved handling symmetry during movement. Trial notes acknowledged the Sten magazine's sensitivity to contamination. Dirt on the feed lips induced misfeeds and stoppages. Gauge blocks checked lip spacing during armourer inspections. The rejected magazines moved to a scrap bin marked unserviceable. The pistol grip used a wooden pattern for familiarity. A small wooden forepiece improved front-end control slightly. Both components attached by screws into threaded inserts. Replacement grips appeared in stores' returns with handling marks. The receiver tube was mild steel of uniform wall thickness. Boring and internal finishing followed standard BSA production practice. Machinists used fixed jigs to hold tubes during cutting. Swarf collected in trays beneath each capstan lathe. Surface finish remained utilitarian rather than decorative. External metal surfaces received a dark protective finish. Trial photographs suggest a parkerized or chemically blackened coating. Records do not specify the exact finishing process used. Barrel blanks arrived as short. The pre-drilled steel rods. These rods underwent rifling in dedicated pull-through machines. Operators monitored torque and stroke counts on mechanical indicators. Out-of-tolerance barrels were stamped and removed from flow. Each barrel extension interfaced with the concentric mainspring assembly. A threaded collar retained spring and guided its compression. Strip diagrams showed minimal discrete parts for field servicing. The objective remained ease of disassembly without specialized tools. The bolt was a simple cylindrical mass with breech face. A fixed firing pin protruded slightly from the front. Extractor and ejector geometry mirrored contemporary British submachine guns. Changes focused less on internals, more on packaging. The sleeve cocking system required careful tolerance management. The sleeve slid over the rear receiver portion externally. Internal ribs engaged shallow grooves on the bolt body. Clearance had to balance smooth travel and dirt tolerance. Inspection sheets listed acceptable radial play between sleeve surfaces. Excessively loose sleeves risked rough cocking and noisy rattling. Over-tight fits led to sluggish operation under fouling. Fitters used feeler gauges to verify assembled clearances. A spiral knurl pattern, improved grip on the sleeve. The pattern extended around the circumference for ambidextrous handling. Operators could pull the sleeve with gloved hands. Friction surfaces were left slightly matte for traction. During assembly, workers lubricated sleeve tracks with light oil. Trial comments mention oil attracting grit in adverse environments. It provided safe and automatic positions. The fire control group provided safe and automatic positions. Some documentation indicates a semi-automatic capability was trialled. Records vary on how many selector variants were built. Surviving examples do not conclusively represent all test configurations. Cyclic rate figures cluster around 500 rounds minute. One detailed technical sheet claims approximately 650. Discrepancy suggests different springs or ammunition during measurements. The design targeted controllable bursts rather than maximum volume. Station 9 staff evaluated the well gun against compact Sten variants. The Sten Mark IV emerged as a principal comparator. Though both weapons addressed concealment and parachute container limitations, both shared the same cartridge, magazines, and basic principle. Trial reports describe the well gun as accurate at short ranges. The central magazine and pistol grip aided controllability. Test firing used standard Mark I Z-ball ammunition in charges. Group sizes met expectations for close combat submachine guns generally. Endurance firing sought to expose weaknesses in feed and sleeve. Guns were fired in extended bursts, then cooled. Bolts, sleeves, and receivers were inspected for peening. Notes mention minor battering, but no catastrophic failures recorded. Another set of accounts reports poor reliability during trials. These likely reference different guns or altered test protocols. Some documents emphasize satisfactory behavior, others stress stoppage frequency. And overall, archival material does not present a single consensus. What is consistent is the absence of adoption. The well gun remained a prototype in limited production numbers. Procurement boards already relied heavily on existing Sten lines. The economic argument favoured current tooling and logistics. Minutes from such bodies typically reference cost and disruption. Retooling for a small incremental improvement appeared unjustified. Stockpiles of Sten components already occupied depot shelving. Factories had trained operators, fixtures, and established inspection regimes. The well gun sleeve demanded new production and gauging fixtures. Sleeve grooves required specialized turning and internal profiling operations. Bolt engagement features added machining steps and inspection points. These factors increased unit cost compared to tube-based Stens. Shipping documentation shows well guns issued only for trial purposes. Serial ranges appear short and discontinuous in surviving records. Some weapons went to training units for user impressions. Others likely remained in controlled stores before later disposal. User handling comments referenced the folding stock mechanism. With stock folded, the weapon carried comfortably under clothing. A simple sling could be retained without major projection issues. The smooth sleeve helped when sliding through tight equipment spaces. Airdrop packing trials placed the well gun in padded containers. The absence of a projecting handle reduced snagging risk. Containers could be narrower, easing loading into aircraft racks. Reduced silhouette also assisted concealment after ground recovery. But field cleanliness remained a continuing consideration in design discussion. Sleeve gaps represented potential ingress paths for mud and grit. Trials in mud pits attempted to quantify this vulnerability. Reports mentioned some stiffening of movement after heavy fouling. Armourers broke down fouled guns on trestle tables. Sleeves came off with moderate effort using manual strength. Bristle brushes cleared recesses inside the sleeve grooves. Solvent-soaked cloths removed impacted residue around bolt shoulders. Reassembly times were compared with equivalent Sten procedures. Well-gun disassembly required no separate tool beyond a cartridge. Time differences were minor and not judged operationally decisive. The sleeve did introduce one extra sliding interface to service. The training syllabus for well-gun users mirrored existing Sten instruction, and safety drills addressed the open bolt action. Recruits were told to grip the sleeve, not receiver. Instructional diagrams highlighted knurling to guide the hand placement. Safety drills addressed the open bolt nature of operation. Operators were trained to verify bolt position visually. Magazine removal preceded dry firing and spring release actions. Sleeve manipulation featured in clearing stoppage routines as well. Clearance drills included feed stoppage, misfire, and double feed examples. In each case, sleeve control prevented accidental forward bolt movement. Trainers insisted on sleeve retention while manipulating magazines. This reduced unintended chambering or firing during fault handling. British Ordnance bureaucracy produced standard forms for every trial, so each firing day generated sheets listing rounds by lot. Malfunctions were tallied under established coded headings and columns. Officers signed off summaries and forwarded them to committees. Well-gun entries occupied lines near various other experimental guns. The norm gun and compact Sten variants appeared beside them. These tables presented weapons as interchangeable cells in grids. No emotive language appeared in these tabulated remarks or decisions. Procurement boards weighed figures rather than individual prototype character. They saw stoppage ratios, production estimates, and training implications documented. The Welgun's advantages appeared marginal against an entrenched Sten system. Logistical continuity often carried more weight than incremental features. Manufacturing planners drew up notional Welgun line layouts. These showed receiver tube machining stations, barrel operations, assembly bays. Additional workstations appeared for sleeve fabrication and fitting checks. Capacity analysis compared these layouts with existing Sten arrangements elsewhere. Tooling lists for the sleeve were longer than for handles. Separate cutters shaped longitudinal ribs and internal keyways precisely. Tool wear projections forecast increased sharpening and replacement intervals. Costs per unit rose accordingly in spreadsheet-style planning sheets. Stock control clerks had to consider spare sleeve provisioning. Each gun potentially required replacement sleeves during its life. Stores would need bins, labels, and ledgers for these spares. The Sten solid handle generated fewer separate spares categories. And shipping crates would need updated packing diagrams for Welguns. Sleeves extended slightly beyond simple tube dimensions when assembled. Crate designers marked out clearances around folded stocks and sleeves. Any change here multiplied across hundreds of containers per shipment. The Welgun offered a smoother handling profile and clothing. Agents moving through narrow passages could keep the gun close. Sleeve operation reduced chances of snagging on straps or belts. These qualities aligned with clandestine operating doctrines of the period. Yet reliability or reputation weighed heavily against any new system. Some reports praised Welgun test performance as fully acceptable. Other sources described disappointing reliability under later evaluations. The divergence may reflect ammunition, maintenance, or individual prototype variation. The designers produced multiple prototypes to refine features incrementally. Minor changes in magazine well angle appear in photographs. Small adjustments in grip shape aim to improve controllability. Sleeve profile possibly evolved as tolerancing data accumulated gradually. Each change required updated drawings, approvals, and distribution lists. Blueprint registers tracked which units held which revision numbers. Misalignment between drawings and actual parts caused administrative friction. Paper-based tracking systems left room for occasional misfiled updates. On the shop floor, inspectors used gauges dedicated to Welgun dimensions. Go and no-go plugs checked receiver tube internal diameters. Ring gauges verified sleeve outer tolerances for consistent sliding clearance. And any out-of-tolerance item received an impact stamp and segregation. Rework instructions guided machinists when defects were correctable. Light polishing could restore acceptable sleeve internal finish sometimes. More severe dimensional errors pushed parts directly into scrap bins. Scrap rates influenced final cost projections in planning documents. Training armurers needed additional notes for the concentric mainspring. Unlike standard rear spring Stens, Welgun springs encircled the barrel. This required slightly different disassembly and inspection patterns. Hands followed alternative sequences when removing fouling and corrosion. Safety considerations focused on unintended discharge during impact scenarios. Open bolt guns can fire if dropped under certain conditions. Testers performed drop trials with inert cartridges fitted inside. Yet reports do not record specific Welgun failures in these tests. Metal fatigue around the sleeve engagement cuts received scrutiny. Repeated cocking cycles concentrated stress in localized receiver regions. Metallurgists examined test pieces after high-cycle endurance rigs. No documented cracking problems appear in surviving accessible summaries. The Welgun's sights were simple and fixed. A front blade aligned with a rear aperture notch. Range settings centered around 100 yards practical engagement. This reflected intended close-quarters use in resistance actions. Materials choices followed wartime availability patterns and constraints. Mild steel dominated structural receivers and barrel blanks primarily. Harder alloys appeared only where necessary for wear surfaces. Wood stocks used commonplace species available through supply channels. Logbooks recorded serials of Welguns transferred to museums post-war. One example now resides within the Imperial War Museum's collection. Its condition shows typical finish wear on high-contact edges. Sleeve knurling remains clearly defined under controlled storage conditions. Measurements taken from surviving examples generally match wartime documents. Small discrepancies likely result from wear or minor production variants. These differences fall within understandable tolerances for hand-fitted prototypes. Records do not describe any major dimensional redesign during development. Special operations executive interest extended beyond simple ballistic performance. Ease of concealment, sound signature, and handling all mattered. The Weldgun addressed concealment and handling through compactness and sieve. Sound characteristics remained comparable to other unsuppressed 9mm submachine guns. Some family weapons incorporated integral suppressors and specialized rolls. The Weldgun did not feature any integral suppression system. Its role aligned more with general-purpose clandestine automatic arms. Silence duties fell to other Station 9 developments and patterns. Standardized forms governed every stage from conception to rejection. Proposals were submitted, annotated, and returned with handwritten comments. Test authorizations carried references to prior minutes and decisions. Cancellation notices used short statements citing comparative disadvantage conclusions. Once cancelled, Weldgun spares and fixtures lost procurement priority. Future contracts went instead to proven production Sten suppliers. Weldgun gauges likely moved into storage crates or scrap piles. Records rarely follow such tooling after project termination decisions. The sleeve cocking system remained largely confined to this design. Later British submachine guns reverted to conventional charging handles. This indicates institutional preference for simpler, established interface solutions. Unfamiliar mechanisms can complicate training and field troubleshooting processes. From a purely mechanical perspective, the Weldgun was serviceable. Its components interacted in a straightforward, understandable sequence overall. Where it diverged lay mostly in packaging and cocking geometry. That divergence incurred costs not fully offset by its benefits. Today, examination of surviving examples requires museum supervision and documentation. Curators note serial numbers, finish, and any post-war modifications. Researchers measure sleeve play, spring tension, and feed geometry carefully. These observations help bridge gaps left by incomplete wartime paperwork. Source basis for technical and historical data.